Hello everyone. In the previous class we have discussed about 4-bit full adder, that is two methods of writing the Verilog HDL code. First method by using the data flow operators, and the second method full adder with a carry look ahead. In today's class we will see the ripple counter. So in the previous modeling, that is in the gate level modeling, we have not discussed this ripple counter, whereas here we are going to discuss this additional example. So we design a 4-bit ripple counter by using a negative edge triggered flip-flop. So in the first module, at very abstract level, we have discussed already this, that is a hierarchical modeling concept. In the hierarchical modeling concept, now we are going to design this ripple counter, that is 4-bit ripple counter, using Verilog data flow statement. And also you can test that by writing the stimulus also, but here we are going to discuss the Verilog HDL program. So the diagram of the 4-bit ripple carry counter module is shown in the diagram. So that figure shows the 4-bit ripple carry counter, which consists of, as it is a 4-bit, 4 T flip-flops, TFF0, TFF1, TFF2 and TFF3 are there. Then clock pulse is applied to the TFF0. So it is a negative edge trigger flip-flop that is identified by that bubble. Then as it is a asynchronous flip-flop, output of the first flip-flop, that is TFF0, the Q of that one is connected to the clock pulse of the next T flip-flop, that is TFF1. So like this, the output of the every flip-flop is connected as the clock pulse to the next flip-flop. So Q0, Q1, Q2 and Q3 are the outputs, and we have a asynchronous clear input. It is a positive active high. It is clear is a active high pin. This figure shows the T flip-flop that is built with a 1 D flip-flop and an inverter. So each T flip-flop, we have 4 T flip-flop, each one of them is going to build with this structure, that is T flip-flop is designed with a 1 D flip-flop and 1 inverter. So here also we are applying a negative edge triggered clock pulse. So same clock pulse that is required here as we have used in T flip-flop, the same thing must be used here. Then a D input is coming from the output with a inverted, that is Q output is inverted and applied back to the D input, and we have a reset or clear. So this is the T flip-flop that is built with 1 D flip-flop and an inverter. And this figure shows the D flip-flop constructed from the basic logic gates, that is a leaf cells. So in a first module we have discussed top to bottom design methodology. So the last cell is nothing but a leaf cell from which we cannot further subdivide. So this is a leaf cell or very basic cell, so which consists of the NAND gates and inverters. So clear, clock are applied, Q and Q bar are the outputs. So this is a negative edge triggered D flip-flop with clear input. Next, this is a Verilog code for a ripple 4-bit ripple counter. So from the diagrams that we have discussed, we write the corresponding Verilog HDL program using the data flow statements in a top-down fashion or top-down methodology. So first we are going to design the module counter. So this is a module counter program. So this code is shown in this example. The code contains instantiation of 4 T flip-flop modules. That means this is a gate level modeling. It is not a data flow modeling, as we have a four blocks in the block diagram in a of a 4-bit triple carry counter that can be implemented by using the gate level modeling. So declaration part will be the same, but it is we have instantiated that those blocks. So module, counter, list of input and output, that is Q, clock and clear. Then IO ports need to be declared here. So output is Q, that is Q0, Q1, Q2 and Q3. So that can be declared as 3 down to 0. So that is a vector output. Q is a vector output which have 4-bit value, Q of 0, Q of 1, Q of 2 and Q of 3. Then two inputs, clock and clear. So according to the diagram, we need to instantiate the T flip-flop. For that we need to refer the block diagram again. So that is this block diagram we need to refer. So TFF is a user defined primitive. As user defined primitive is used, it is not a predefined primitive. The instant name is compulsory here, that's why TFF0. So for TFF0, what are the inputs and outputs? So the output is Q0, then input is clock and clear. So as we have declared the output Q as a vector 3 down to 0, it is going to be Q of 0, comma clock, comma clear. Similarly TFF1, instantiation of the second flip-flop. So its output is Q of 1, then input is from the previous output, the clock pulse is applied, that is nothing but a Q of 0 is applied as a clock pulse. So Q of 0 is going to be an input for TFF1 and clear is the common input for all the flip-flop. Similarly TFF2, so its instantiation is Q of 2, comma Q of 1, comma clear, and TFF3 is Q of 3, comma Q of 2 and clear, end module. So this is a module counter. So this is a 4-bit synchronous counter with clear and count enable. You can also have the count enable input also. Now see here, this is a Verilog code for T flip-flop. Now this T flip-flop is again done by using the gate level modeling. So that is for this diagram T flip-flop, in which we have a D flip-flop and an inverter. For D flip-flop we have a clock input and we have D input and Q output and also a reset input. So module T flip-flop, the list Q, clock and clear. The output is single output, that is Q, and inputs are clock and clear. Now give a name for the instantiation, edge D flip-flop, flip-flop 1, that is FF1 is the instance name, Q is the output and not of Q is also a output. So we have two outputs for the T flip-flop. One is direct form and another one is the complement form. So Q and not of Q. So only one declaration is only one, but it is original form and its complemented form, both are used here in the output instantiation. So Q and not of Q are the outputs, clock and clear are the inputs. Clock and clear, only one block is there, that's why instantiation is very easy. So end the module. Now finally we are going to write the Verilog code for edge triggered D flip-flop using data flow modeling. So for edge triggered D flip-flop, module edge D flip-flop, the list of input and outputs are Q, Q bar, D, clock and clear, and output, declare the output and inputs Q, Q bar, input is D, clock and clear. You can declare the wires of again you have to refer the circuit diagram. So wires are S, S bar, R, R bar and C bar. You can see the figure. So see here, clear, clock, D are the inputs, Q and Q bar are the outputs. Then we have intermediate wires, C bar, S bar, S, R and R bar. So these are the wires. So those are declared here. Wire S, S bar, R bar and C bar. And 5 input and output together, that is Q, Q bar, D, clock and clear. So this is the declaration part. Now the logic part. Assign C bar is equal to not of clear. Observe the diagram. Again here, input is clear, output is C bar. So we in a data flow modeling, we need to use the keyword assign. So clear is the input, C bar is the output. So how to write the code for that one? Assign C bar is the output is equal to not of clear. C bar is equal to not of clear. So this is how we are going to write the statement using assign statement. So C bar is equal to not of clear. So clear is the input, it will be complemented and assigned to the output. Then assign S bar is equal to not of R bar and S. Observe the figure. S bar is a NAND gate. So its inputs are, one is from S, another one is from the R bar. Observe the lines for S bar output. So S bar is the output, its inputs are R bar and another one is S. That's why assign S bar. So this is a NAND gate. That's why NAND gate symbol is tidal sign followed by AND operation. Together it is a NAND. That's why R bar and S. So R bar and S performs the AND operation. To make it NAND, just complement it by using a tidal sign. So this is a S bar. Similarly, observe the figure for writing S, R and R bar. So S, R and R bar, again we have a NAND gates. So the inputs for S is S bar, C bar and the complement of the clock, that is negative edge, and all together it is complemented again to get the NAND gate output. Then R is equal to not of R is equal to, the inputs will be R bar and not of clock and yes. Here again to get the NAND output, the all together is complemented by using tidal sign. So this is R. Similarly, R bar is equal to R and C bar and D to all together complemented to get the NAND output. So now the termination sign. So this assign is going to be going to use for 4 statements: S bar, S, R and R bar. And finally assign Q is equal to S and Q bar and AND of that one by using the complement operation. And Q bar is equal to Q and R and C bar complement of that one to get the NAND gate, the end module. So assign Q and Q bar, just we will see the diagram. Q and Q bar. Q, the NAND gate output is Q, its input is coming from S and the Q bar, and the Q bar is the one more output, its inputs are coming from 3 different sources. One is from the Q, another one is from the C bar and another one is from the R. So that's how the code is written here. Q, R and C bar all are ANDed and complement of that one will be unANDed, end module. Now you can also write the, this is the design. Then you can also write the instantiation of a design block inside the stimulus block to test the design. So when you execute this program, you can write the test bench for this one or stimulus block and verify the result. Thank you for watching the video.